Welcome to lecture 5 in week 5 of machine learning foundations. We are continuing the discussion on the linear algebra side of things. In this particular lecture, we will be able to prove the most important theorem that we wanted to get to, which is the spectral theorem, which in essence states the following. A Hermitian matrix is unitarily diagonalizable. Do note that this is not an if and only if. So, if a matrix is unitarily diagonalizable, that does not imply that matrix is necessarily Hermitian. All we are saying is that if a matrix is Hermitian, then it is unitarily diagonalizable. Now, an important corollary of this fact in the context of real vector spaces is that a real symmetric matrix is orthogonally diagonalizable. That's the version of spectral theorem for real symmetric matrices. We'll prove the spectral theorem for complex matrices for Hermitian matrices by using what we proved in the previous lecture, which is Shor's theorem, which actually stated that every matrix is upper triangularizable. We'll use this fact to show that Hermitian matrix is unitarily diagonalizable, and then a few examples after that.
Now the main theorem, so-called spectral theorem. The most general case, this says that any Hermitian matrix is unitarily diagonalizable that is U star, that is there exists unitary matrix U such that write it like this. A Hermitian matrix A is unitarily diagonalizable, that is U star AU is diagonal a diagonal matrix with real numbers. The proof is very simple given Shor's theorem. From Shor's theorem, what we have is you have U star AU is an upper triangular matrix. Now let's look at T star. This is U star A star U, but this is the same as U star AU because A equals A star. It's a Hermitian matrix. Now, but U star AU is just T, just by construction. Now, T is a upper triangular matrix. So, what is T star? T star would be a lower triangular matrix. So, if you have T here, T, then you have 0 here. And then when you take its conjugate transpose, T star would just move all the entries above the diagonal below. Okay. Now T equals T star, that can only happen if T is diagonal. Okay, so we have T is a diagonal matrix, so U star AU is equal to T where T is a diagonal matrix. But this is not all. We also claimed that the diagonal entries are just real. So let's also show that. Now T equals T star implies, if you consider just the diagonal entries, Tii equals T star II. This is the, but this is the same as T bar II plus Tii is a real number. Okay. So the final claim is U star AU equals T with T denoting a diagonal matrix with real entries. So that's where the proof ends. So let's look at an example. It's easy to check that A star equals A. What is the characteristic polynomial of A? P of lambda equals lambda minus 1 to lambda minus 4. And so the eigenvalues are lambda 1 equals 1, lambda 2 equals 4. It's a very simple matrix, so I'm just going to write down the eigenvectors. Eigenvectors. Let's call this Z1 equals minus 1 plus I, 1, corresponding to lambda 1, and Z2 equals 1 minus I, 2. It's easy to check that Z1 bar transpose Z2 equals 0. But we need a unitary matrix, so we need to do a little more work. So just normalize. So normalize Z1 comma Z2 to obtain U1 is just the normalized version. So it's minus 1 plus I divided by square root 3. We'll write this 1 by square root 3. U2 equals 1 minus I divided by square root 6 and 2 divided by square root 6. And then let U equals U1, U2. Then what is U star AU? U star AU can be verified to be the diagonal matrix with these entries. A very important corollary to the result above, important corollary to the diagonalization result is the following. So the real world counterparts of Hermitian matrix is a real symmetric matrix. A real symmetric matrix A is, and the word in the real world, instead of the unitary, concept in a complex vector space is orthogonally diagonalizable. That is, there exists a matrix Q such that, instead of U star AU, I'll take Q transpose A Q, and I'll get a diagonal matrix. Q transpose Q is identity because that's an orthogonal matrix, and this is a diagonal matrix with real entries. This is the spectral theorem. Yeah. This is the spectral theorem. I mean, the proof is fairly straightforward. I'll just give it to you. Okay. From the claim for Hermitian matrices, we have U star AU equals U inverse AU equals D, a diagonal matrix, and columns of this matrix U are the eigenvectors of A. That's given. Now it's clear A is real symmetric, which is saying that it's Hermitian, implies eigen values of A are real. So if I look at A minus lambda I times x equals 0, now solving leads to a real vector x, and this implies U is a real matrix, or U trans or U star equals U bar transpose equals U transpose equals U inverse. That's all there is to it. Hence we have U transpose AU equals diagonals with U transpose U equals. I'll end this topic with one final remark, which is the following. We have Hermitian matrices are, if a matrix is Hermitian, implies it is unitarily diagonalizable. But this does not mean that the only unitarily diagonalizable matrices are Hermitian matrices. In particular, the converse is not true. So to see this, consider a simple matrix such as 0, minus 1, 1, 0. It's easy to see that A star is simply not equal to A, but you can always find enough eigenvectors. So the eigenvalues lambda 1 equals I. You can just check this. Lambda 2 equals minus I. This already implies distinct eigenvalues. Implies A is diagonalizable. And the corresponding eigenvectors are Z1 is 1 minus I, Z2 is 1 I. You can normalize it. Normalizing just two vectors, so it's easy. So U1 is just divided by the length of the vector. So 1 by square root 2 minus I by square root 2. And U2 is again 1 by square root 2 I by square root 2. Now all you have to do is write this matrix U, U1, U2, and you can check that U star AU is I 0, 0, minus I.
A recap of what happened in today's lecture. What did we learn today? The first thing that we understood today was we could we could state and prove the following claim, which is a Hermitian matrix is unitarily diagonalizable. Now, this result in the context of real vector spaces states that a real symmetric matrix is orthogonally diagonalizable, which is a very important result. Also, which is well known as the spectral theorem. And now we did a few examples to verify this fact for a complex matrix as well as a real symmetric matrix. In the complex case, we took a Hermitian matrix and we could unitarily diagonalize it. And lastly, we actually exhibited a matrix which is unitarily diagonalizable but which is not Hermitian. So please do understand the claim well. If a matrix is Hermitian, yes, it is unitarily diagonalizable, but the converse is not necessarily, converse is not true. So there are matrices which are not Hermitian but still unitarily diagonalizable.